What is the limit of soft robots to adapt to uncertainties like damage? And what does it take to achieve fatigue-resistant soft material? Is it about material properties or morphology? An evolutionary term is certain creatures have already figured out how to do that. And we ask, what are the missing pieces to enhance soft materials' toughness? In this podcast, I'm sharing my passion and curiosity for soft robotics, where we share inspiring stories about the work we do and how we can push the limit. I am Mara Dwayne, and this is Soft Robotics Podcast. So first of all, congratulations for the new paper in Science. And I think it's very interesting, and I really like this topic because I'm so passionate about what you're doing, especially in fatigue-resistant elastomer. But maybe the first question I would like to ask you, why it's so hard to design both stiff and tough material, soft material? Why is it challenging?
Okay, what's the challenge? Now, for soft material, we're very specific. We're talking about materials with a polymer network, covalent polymer network. The reason we want to have a covalent polymer network is for application requires some permanence, such as the soft robotics. You don't want material keep evolving, change properties as you use it. You want material property to be stable. So the way to do it is to have a covalent network, right? Mm-hmm. So now, if there is a well-known conflict for covalent network elastomer or hydrogel. It is if you make a chain short with a lot of crosslinks, then the material becomes stiff. That's what many people want. But if a chain is short, the material is brittle. The other way around, if you make chain long, the material becomes soft. The material is tough. So there is a conflict. It's recorded in quite a few decades. People know that fact. So that is the conflict.
Mm-hmm. Great. So I'm curious to ask you the kind of questions that lead you to come up with design for Tinglemer. I don't think you said that term, but it's not in the paper, right? How you came up with this design, or because you thought it doesn't make sense at the beginning, people thought it doesn't affect on toughness.
Yeah, so that when for the last 2 decades, many people have tried to make hydrogel in particular. So that's how we got into the field, start with a hydrogel, how to make hydrogel tough. So the idea pioneered by Professor Jianping Gong in Japan is to introduce the sacrificial bonds. So in addition to a covalent network, her material has another network. For many years, she and other people study this material she's discovered, and felt that the sacrificial bonds can enhance toughness by sacrificing themselves. Essentially, as a crack grow into the material, sacrificial network breaks, but another network doesn't break. The broken network dissipate a lot of energy that adds to the toughness. So that has been strategy. Many people, including ourselves, have been using that strategy for essentially 10 plus years. So the conclusion is at the time was if you want to have a tough hydrogel and also maintain some stiffness, then you really need to have the sacrificial bonds. But the problem with the sacrificial bonds, people also realize it, is problem of fatigue. And also because it's sacrificial, then after first cycle, you probably already sacrifice many bonds. Then the second cycle, you do not benefit of these sacrificed bonds. Then this lead to other things people talk about. Oh, how about we do self-healing? We sacrifice you and then waste a little bit and heal. But healing takes time and the material system become more convoluted. So that hasn't led to any real breakthrough. This is self-healing idea. It sounds good idea, but no real, really good system yet. So, so that was a situation. Yeah, the situation became very clear when we started to study fatigue of hydrogel. So my group, there was a Chinese visiting student. In 2017, we published the first paper on fatigue of hydrogel. Before that, people, for some reason, didn't really study fatigue crack growth in hydrogel. So, and we find that, for example, polyacrylamide, that was a material we use, appeared to be quite elastic, but somehow still suffer fatigue. That got us into the field. We also tested, I guess more dramatic cases, we tested some of the tough hydrogel. The tough hydrogel with a toughness going to 10,000, almost 10,000 joule per meter squared. That's a toughness, meaning you grow a crack under monotonic load, how much energy you need to extend the crack by unit area, about 10,000 joule per meter squared. But then we do cyclic loading. The crack can grow cycle by cycle. When energy, the load is only about 50 joule per meter squared. Right? So that means the material suffer fatigue. So the material is very tough when you do single load. When you do cyclic load, it become, the crack can grow at a very low load. So that was a paper also published in 2017. So that led us to feel all these sacrificial bonds ideas at least need to be re-examined under the cyclic load. Subsequently, many groups entered the field, re-examining this. Fatigue crack growth in mechanical engineering has been, many decades. People test all kinds of materials, starting with the metals and the plastics and also elastomers. Incidentally, if you test fatigue of natural rubber, that's a classical example, first tested in 1960s. People discovered, rubber gives you a sense of very tough material, wonderful material, nature's standard. But if you under cyclic loading, the fatigue, what we call the fatigue threshold, the energy at which crack can start to grow, it's also about 50 joule per meter squared. That number has not been improved for natural rubber for all these decades. After people doing so many things to natural rubbers, that number has not been changed. So yeah, when we discovered our hydrogel has a 50 joule per meter square threshold, we were stuck. So we say, okay, we create a material very tough for one load, but for cyclic load, it is brittle again. Yeah. So that was 2017. 2017, you are asking what led us to this recent discovery. The discovery was made by a student, PhD student in the group, coming from Korea. His name is his first author, Sun. No, sorry, Kim. Sun was a previous Korean student. Junsu Kim. Yeah, he conceived this idea. Now, what led him to this idea also itself, because we were so obsessed with the fatigue of a hydrogel. We tested many materials. I already mentioned we tested our own material. Would give you 50 joule per meter squared. And then we tested the material created by Zhenping Gong. So the testing was done in the lab in Xi'an Jiaotong University, led by my collaborators there. So of course we just communicated through the internet. We have been collaborating for many years. So then student is a lady. Her last name is Zhigang. She, at that time, a new student, didn't know this is a long time mechanical issues in mechanical engineering. This is just one project for her. And she tested. She found Zhenping Gong's material has a threshold, fatigue threshold. Initially it's 400 joule per meter squared. Afterwards, we did more tests, more careful tests. It become 200, 300, but it's in the hundreds. What's important to us, why this number is much higher than our own material developed by us. What's the secret thing in Zhenping Gong's material? We first have to learn her recipe and make her material in our lab. These materials are laboratory material. You cannot order online. You have to learn from the paper and just reproduce these materials. So you can imagine this conversation is just online. We use chat thing, just one chat going there, another chat coming back. We sometimes go just like this, go on a video conference, keep talking about it, back and forward. We had no clue what was going on. And then finally, we compare her material with our material. We found the difference is, so both materials have a double network. So the primary network has a very long chain. Ours have a long chain. Her material has even longer chains. So we didn't notice about this before. So our second network, our material and her material are different. But the primary, just a long chain network, our same material, polyacrylamide, but her material, just for whatever reason, has a very long chains. So that is ultimately we decided that is a reason to have high threshold. Now, this conclusion was reached actually many decades ago by a paper, Lake Thomas, you probably heard this, called Lake Thomas model. So they have this picture at that time. The paper was published in 1967. It's a well-known paper in the field of elastomer and hydrogel, and well-known to us as well. But I guess we didn't really settle down, this message did not settle down in our head. So until we actually try to calculate things. So now the key picture is the following. It's an intuitive picture, Lake Thomas picture. The picture is the following. If you have a network, with a chain of some length. and then you have a crack coming through the material. So for crack to advance, you need to cut chain, one chain at a time. You just cut these chains, crack. You load it outside. So before a chain break, the chain only break at a single covalent bond. But before this chain break, the entire chain is stretched taut all the way to the breaking point, near breaking point. That's a lot of energy stored in the chain because the chain is long, more than single atomic bond. When you break a single bond, the entire chain snaps, and the energy stored in the entire chain is released. That's the message of Lake Thomas model. In the past, we only focus on formulas. We know this picture, but the importance of this picture did not sink in. So what you really need to do is have a very long chain. Also allow the stress to propagate through the entire chain. The reason elastomer and hydrogel can do that is because of this one long chain and adjacent chain has a very weak intermolecular interaction. So a stress can propagate along the long chain before they go to neighboring chains. So this picture, after we realize it, gradually we begin to call this a principle is a stress deconcentration. You need to deconcentrate stress from a single bond to large length in this case, or large volume, whatever you do. You need to deconcentrate the stress. This can be compared to the classical picture of a Griffith. When Griffiths look at the crack growing in a glass, silica glass, you break an atomic bond, that you only snap one bond. So the neighboring bond, there's no chain, right? Neighboring bond just relax elastically. There is no, you only dissipate energy on the order of a single bond, not along the entire chain. So this stress deconcentration idea that we'll talk about this later lead us to many other things, more than molecular material. It could be composite at a higher, larger length scale. But in any case, so when around the time, Zhensu made this connection. So all these ideas we already studied and we understood. We create several other versions of materials. And also in the literature, other groups begin to create materials. So we can talk about these as well. So essentially it has already enhanced threshold 2000 from 50 to 100, then 2000. Once you understand the mechanism, so then engineers, right, want to do things to amplify the mechanism at all costs, initially anyway. So the fatigue-resistant material by that time, when Zhensu conceived her idea, was already, so we understand it, other people also begin to understand it as well. Then Zhensu has been looking at hydrogel for various things. Then one day he came to my office. He is a very bright student. Even before conceiving this idea, we all know he's bright. So one day he came to my office, explained this idea to me, that you can use a single network. So now we already know a single network, if you have very long chains, you enhance fatigue threshold. That's very good. But the material becomes very soft because the chain is very long. It's known as a modulus scale with the inverse of a chain length, So, but he said, look, if I can make these chains have a lot of entanglements, very long chains, but lots of entanglements. Now, it's also known in the literature, highly entangled material has high stiffness, because as far as stiffness is concerned, you can picture in your head, it's the entanglement is as effective as crosslinks. Effectively, you make chain very short. So that's from stiffness point of view. However, from toughness point of view, this tension can go along the chain, entire chain, also over the entanglement, because entanglement can slip. So the high tension can still propagate along the entire chain. If you have a long chain, when a chain break at a single molecular bond, the entire chain will release energy. So he presented idea so clearly. It was just like that. So I immediately understood. The rest is just how to test this idea, do various experiments. The guy is also very hard worker, very hard worker. He recruited other people, but he was really the driving force to test this idea. Immediately we felt it was a powerful idea. So initially it was not thinking about how to make fancy materials, just to test this idea. So it's very straightforward, right? You want to make this material and measure stiffness and also measure toughness and show both are high. That was that. So along the way, he also discovered when you make this hydrogel with lots of entanglements, the material has almost zero hysteresis. Zero means so hysteresis means that your stress strain curve going up, stress strain curve going up. When you unload, the curve is lower than loading curve. But our hydrogel, the loading curve and unloading curve almost coincide. So then if you magnify it, you can see a little separation. That separation, the area, is about 1% of total stress strain under stress strain. That's remarkable, even better than natural rubber. Natural rubber is a few percent. So the reason is known, at least we feel that's the reason, just because hydrogel, you have a lot of water. Water has such a low viscosity. So even entanglements cannot increase internal friction. Right? So now then you have a material highly elastic, very desirable among robotics people. I don't want to have a material dissipate all that energy. So before material fatigue, the robots will get fatigued. Highly elastic and also stiff as other hydrogel, and much tougher than hydrogel. So then essentially for the first time, you have a homopolymer has both these attributes. That's very unusual.
That's really wonderful. I would like to ask you many questions here. Maybe the first thing about the design, because based on what you mentioned, for example, that sometimes maybe we lack understanding how we can merge the two, and finally you did it with your team. But I'm curious about the design, and in that case about the entanglement, do you think it's kind of intuition to come with the design? Because I think this is very important about the solution. For example, okay, if we don't have a material with high toughness, for example, or just to resist the fatigue, go for self-healing, but still it doesn't solve the problem, as you mentioned. And that leads me to the way of thinking of the problem and the design. Is it intuition? How the proper design in that case that really lead to answer the real question in that case? It was intuition?
Yeah, it's a combination of scientific understanding and intuition. because a scientific understanding is a essential Lake Thomas picture. You have to put this picture in your head in its essence, meaning stress is deconcentrated over long length, cannot just stay with a formula. If you have a formula that, yeah, for all these years, we and others have a formula that doesn't help to translate into slightly different situation, because slightly different situation, you don't have formula. But once you understand the essence, then the formula doesn't matter anymore. So, that's scientific. The intuition comes in the following way. That really I have to give credit to Junsu. It's about intuition about what kind of a system you can put together to realize this thing. So many people in the group, many people working with us understand this message of Lake Thomas very, very well, but only Junsu has this idea. I didn't have this idea. Other students and collaborators don't, but Junsu proposed this idea, right? So he has the intuition. So the way he makes a hydrogel is interesting. This is his proposal from very beginning. So I just asked him, okay, how do you make your hydrogel to have a lot of entanglement? Ultimately, we establish how many entanglements you have. So you have a very long chain. So here at one end of the chain, you have a crosslink. Another end of the chain, you have another crosslink. In between, you only have entanglements. How many entanglements between these two crosslinks? About 100. How do you actually do that? So initially, we just say, do as many entanglements as you can. How do you do that? This is his idea. So he said, first of all, I need to have really very long chains in order to have a lot of entanglements. If you have short chains, you cannot have many entanglements. All right, so then he noticed that ordinarily, when you prepare a hydrogel, hydrogel typically has 90% water by weight, 10% polymer, roughly. So what people do is you start with monomer, for example. Start with monomer, the monomer become polymer, and then polymer crosslink into a network. So people say, if I want to have a 90% water, 90% water in a hydrogel, then my precursor should have a 90% water in the hydrogel. This is what people do, 90% water in hydrogel. As a result, your polymers are very far apart. They cannot really entangle. Then Jinsu said, oh, let me do the following. I put minute amount of water in the precursor. So I just give you a concrete number. We're talking about a molecular ratio now. So ordinary hydrogel, maybe you have a 20 water molecule per polymer monomer. And what he did is two water molecules per one monomer. That's an enormous reduction in amount of water. So as a result, the monomers are very crowded together. So as they grow into a long chain, they of course entangle together. If it's so crowded, then they crosslink. He also put tiny amount of crosslinker, much smaller. So typically, yeah, this is another important thing. In the past, people put, if you make a single network, typically you put maybe 100 or, for 100 or 1,000 monomers, you put one crosslinker. So the chains are not too long. But in Junsu's case, almost 1 million monomers, and you put one crosslinker, or 100,000. So 2 orders of magnitude higher, 2 or 3 orders of magnitude higher number of monomer. As a result, you have a very long chain. They're still crossing, and you have many entanglements. So that came from intuition, right? To this day, people, we don't have model because nobody make material his way. We didn't have a scientific model for that. But intuition, this should work. But the guy had that intuition and put things together. So in hindsight, many of these breakthrough, in hindsight, everything is very logical. So when you read a paper, the paper is very logical. But this process, why he wants to do that, how he did that, that it's very difficult to say. Yeah.
Yeah.
Yeah, it's not really, it's kind of by design, but design is just one element of it. Because many people know all the principles, but they do not make the step.
Yeah, yeah. That's great. And that leads me to the question. I think that also your paper, I think 2019, fatigue resistant elastomer, using the lattice, one of the example, moving from the molecular level to like bigger scale. I'm curious to ask you, because you mentioned at the beginning bonds to sacrifice energy. Sometimes it doesn't work. And when I'm looking to the design of the lattice, do you think adding weaker connection in the material to deconcentrate the stress, is there a limitation? Do you think always necessary that you combine the two different material? Is always necessarily increase the toughness, or maybe it could weaken the toughness? Because I'm really curious about this point, the design, when you try to integrate bonds that sacrifice or weaker connection, what is the limitation? Because it seems sometimes it doesn't work. It could weaken, not strengthen. Do you agree with that or not?
That we have, so my field, almost from my PhD thesis time, really is looking at the fracture of composites. So when I was a graduate student in 1980s, I worked with a group of people in developing ceramic matrix composite. So that is not even soft material, ceramic. At that time, what people want is material can sustain high temperature, can put into the engine. So if you, in the engine, you go to high temperature, the burning will be more complete. You have a less environmental issue. Also, it's more efficient, energetic efficiency, Carnot efficiency. Want to go to high temperature in your engine. But the metal cannot go to very high temperature. The best material you can do is ceramics. Ceramics can go to thousands degrees C. So, but ceramics are brittle. Ceramics are brittle, right? So now at that time at UCSB, I worked with the people at UCSB. I was a student at Harvard. So the leader at UCSB is Tony Evans. He led large team, many investigators, to develop ceramic matrix composite. The idea was old, but a lot of technical issue. So through that work, I learned from these people what is the essence of making ceramics tough, right? Ceramics itself are brittle. How do you make ceramics tough? So this idea is the following. Most people don't know the idea. It's like okay. Let me just describe this idea. So ceramics itself is brittle. It's just like a glass is brittle. When you have a crack going through ceramics is a very elastic material, right? So and the stress is concentrated to single atomic bond. You break that atomic bond, you dissipate energy of that atomic bond. The energy in the material, other bonds do not really get dissipated, just elastic. So that's why ceramics is so brittle, or glass is so brittle. All right, so you have just homogeneous ceramics. But now in ceramic composite, you have a fiber, ceramic fiber. But ceramic fiber itself is also brittle. It's another brittle material. You put two brittle materials together, fiber, ceramics, and matrix is also ceramic. Both are ceramic, so both can sustain high temperature. Both very elastic, that's fine. However, you have a very weak interface between fiber and the matrix. So now you can see, if you picture your fiber like our polymer, so you can see that's Lake Thomas again, right? We never called this Lake Thomas. Thomas, yeah, in the theory for composite has a lot of people working on it. They never really connect to Lake Thomas model of an elastomer. It's us. These are the same thing, just different materials. So the point is now you have a fiber. So incidentally, if you make a thin fiber, in this case, maybe micron in diameter, if you make a thin fiber of a ceramic, it can be very strong, meaning it's still elastic, but you need to have a high stress to break it. Right. So, and then this fiber is in the matrix with a weak interface, so that when crack coming to this fiber, want to break this fiber, before this fiber is broken, very long length of a fiber is under high stress. Stress is deconcentrated along the length of fiber. And then this fiber break. When this fiber break, long lengths of fiber release energy. Same story, right? So that's a ceramic matrix composite. You ask how weakness contribute to toughness. So in this case, actually in all cases, the weakness between interface is introduced so that you can deconcentrate stress over long lengths. If you have this mechanism, you have a high toughness.
So clear. Yeah, yeah. But I'm curious to ask you in that point, do you think we can still push the limit of selecting certain design? You mentioned this lattice design. Do you believe that maybe there are other consideration, I don't know, based on intuition, whatever, to make the design more tougher, for example? Which do you think, besides, of course, the material part, do you think the architecture of this integration, do you think there's a room to push more and maybe coming up with new designs?
That's an excellent point. I believe new designs are possible. But among existing materials, once you realize this is a principle, to get high toughness, you can survey the existing material. In my recent talk, I mentioned quite a few materials. Let me say, for example, for many, many decades, people know the following fact. We already said solid glass is very brittle because the stress is concentrated at crack tip to atomic scale, right? Now, however, people also know if I make fiber glass and weave fiber into a fabric, you just have a fabric of glass with no matrix. So fabric is held together by friction, slight friction between fibers. This fabric is tough. Okay, for same reason, if you want to grow a crack into the fabric, then the crack coming to a fiber. So then before this fiber break, long lengths of fiber will be under high stress because in between fiber, the interaction is weak just by friction. It's much weaker than the strength of fiber itself. So, and then after fiber break at a single plane, the long lengths of fiber release energy. So in summary, we understand solid glass is brittle, but a fabric glass can be tough, is tough. So this is a fabric. Then you say, okay, fabric is one structure. We wear fabric. It's not glass fabric, but a similar principle. But fabric cannot be used in many applications. For example, if I want to have something, not only you can wear, also you need to contain gas or liquid. Then since the fabric is not good enough, you need to have a matrix to block that. So then in the matrix, you put matrix. For example, there's a ceramic matrix composite has the matrix because you're making engine. Engine need to contain chemicals, contain fire. You cannot just do a fabric, right? So you need to have a solid piece. So you need to have a matrix. In this case, to protect, so matrix itself is a ceramic, also weak, right? So protect the matrix, you need to have a weak interface, allow interface to slide. Right? So that's a ceramic matrix composite. So for many years, we know you need to have a weak interface to make it tough. Incidentally, in early days of development, people discovered when ceramic goes through high temperature, the interface can sinter together, no longer weak anymore, sinter together. Then ceramic become brittle. The matrix sintered into a whole block of solid, cannot slide anymore, cannot deconcentrate stress anymore. This become brittle. So that's a ceramic matrix composite. Now, then okay, then people also have a polymer matrix composite, right? So we have carbon fiber, very stiff, and the polymer matrix, very soft. So in that community, it's a totally different community, developing polymer matrix composite for airplane, body, and engine are another group of people, ceramic, right? So for polymer matrix composite, people always say, you really want to have good adhesion between matrix and fiber. So for many years, I didn't understand. It was through recent time I studied these elastomer. It dawned on me. Both are coming from the same principle, weak interface, strong weak interface. That's not the point. The point is how you deconcentrate the stress. Because with the polymer composite, matrix composite, the matrix is very soft. So the fiber between fiber has a weak interaction because the matrix is soft. You don't need to have a weak interface anymore. You can still deconcentrate stress along the fiber when a crack comes, right? So of course, once you have this intuition, you look at the formulas. Of course, formulas said that, but the formulas never really settled down in our brain. Even though I worked with both materials in my career, in the past, I did not reconcile these two pictures. Of course, also both pictures are consistent with the Lake Thomas picture of single polymer, though has nothing to do with whether you are polymer or macroscopic, or whether you are ceramic or hydrogel or elastomer. Doesn't matter. You need to deconcentrate stress, period. Yeah. If you have stress concentration, you're brittle.
Yeah. But I'm just ask you, in the percentages of the material, you mentioned sometime that it should be always significantly different material. Do you think if we make the fiber, for example, more soft and the matrix more stiff, would it make any difference in the mechanism to deconcentrate the stress? This kind of percentage, what could be soft and stiff, this combination, should we always be switched? Would it make any difference?
Soft matrix, yeah, that's a good point. So I don't know. Then your load is so maybe let's describe something we actually tried that worked. So we have tried a lattice. Other people have tried lattice as well. So for example, you can just make a lattice material. In mechanics, it's called a truss. You have one element another element like a bridge, elements with a lot of open space. So then when crack coming in, you need to break one member of the truss at a time, right? Before that truss member fail, the entire member has the same stress. When it fail, you release the entire energy of that member. So you have deconcentrated from a single atom to entire member of truss. For the bridge, that member of truss is a meter size. It's enormous, much more than a single atom. So that is a very tough structure. So now you say, okay, I'm not making a bridge. I want to make a material that can block fluid motion. So then you need to have a matrix, right? You need to have a matrix. In that case, we use a soft matrix. Use a soft matrix. Then you say, oh, I really have an issue now because I need to contain gas under cyclic loading. So yeah, I know fiber is good, strong, but this matrix also needs to be fatigue resistant, right? Otherwise, I'll break the matrix, the gas will leak through the matrix. So that means you need to have a soft matrix. Once you are soft, you can have a very long chains, again, that can be fatigue resistant. Now then leads to other issues. If your lattice has a very large open space, and you fill that open space with the soft things, then the water liquid can tunnel through this soft material, right? So then leads to other considerations. So it's a never-ending game, never-ending game. You talk about design. So you're right, there are design principles, but because of this space, it's very nonlinear with all kinds of sizes. We don't really have a package theory. Just we have a list of insights people know about. Every time we learn, we add to our insight. They're not really connected through equations or through checklists. We don't really have that. But people do design based on these ideas and test it out.
Yeah, I think maybe I'm just asking you, do you think it's risky to go for space? Because it seems we still try to understand, as you mentioned. Do you think it's so risky to go for these ideas and try to explore and push the limit of the design for example, using, fatigue-resistant design? Do you think it's so risky?
Well, yes or no. Any new material, you need to have a lot of experience before you use for very critical application. So for example, this polymer matrix composite was conceived soon after synthetic polymer became available in 1960s. People already conceived that idea. Oh, this is an obvious idea. At that time, it's not about fatigue. It's an obvious idea. I can have a strong, stiff material with a fiber, and but tough. It doesn't break easily. So that's 1930, 1940, right? But that material was implemented after so many decades, into aircraft, I believe, in 1990s. After 50, 60 years, you implement in critical application. Ceramic engine was the same thing. Ceramic engine, before us, I got into the field in 1980s, but the field already started in maybe 70s or even early 60s. People already had this need and conceived that idea. They didn't call it a stress deconcentration. They just say it's called a shear lag effect. Shear lag effect. It's the same idea. So now, but so when I got the field, the vision was already crystal clear, but it was still a vision. We did research. So many of us, almost all of us, left the field at the university because we didn't have funding anymore. Industries are not using that material. they were not using that material. So, and the government said, okay, what is the research issue? Wasn't clear what's research issue anyway. We already solved the issues we know about. So 1990s, I left the field in 1990s to move on stretchable electronics. So I couldn't stay in the ceramic composite field anymore. No funding. And then in 2000, around 2000, the materials will actually get used I believe now it's used as an engine for some of the aircrafts, replace metallic engines. It's used. So after decades of research.
Yeah.
Now, I guess in this soft materials is interesting because the material itself is cheap and many applications are not really critical, right? So what? A soft robot failed. You study a soft robot. So maybe can have more people try many things. Maybe you try many things that look like you adapt, you change, you evolve. So maybe development can be faster. But many people are also look for more mission critical applications, such as a heart valve. Then that thing is critical, cannot fail. Cannot fail. Yeah.
Yeah. So maybe we can take one question from the audience. Purvis asks us, what length scale is required in order to gain the friction and fatigue toughness benefits from entangled elastomer? In your paper, you showed that 50% strain without propagating a defect. Does this imply that small structure could be fabricated by stretching the material and cutting in a stretched state, then revealing the strain? How would you approach bonding such material so that the desirable bulk properties not be defeated by fatigue or fracture at the interface?
The scale, there's a principle of deconcentrating stress. That scale now we show, as the people show, start from molecular scale. So you can start with individual polymer chain, deconcentration stress along the chain, individual chain. That's molecular scale. And we go up, we can make, we mentioned this polymer matrix composite, ceramic matrix composite. That's a scale at a fiber. The fiber is on the order of 1 micron in diameter. So length of fiber could be longer. So that scale also worked. Then people also make even larger scale. So for example, bridge has this truss structure. Each truss member is on the order of meter. That also works. So that basic idea of a deconcentrating stress is works on all scales. However, there is a very important subtlety. We don't get a chance to study it carefully. So if you look at a ceramic matrix composite, right? Ceramic matrix composite. So the toughness, if you have a fiber with a bigger diameter, then you can deconcentrate stress over longer length scale. So then the stress, the energy stored over larger volume. That seems to say, okay, you maybe want to have a fiber of a bigger diameter. Why not a millimeter diameter? So there are some manufacturing issues, but just from a mechanical point of view, there's another issue. If you make a fiber very big, the strength of the fiber, somebody is cleaning the yard, the strength of the fiber reduces with the volume. So people have known this for many decades. Thin fiber, same material, thin fiber has a higher strength. So then it's a matter of a try and error. So you want to have a larger microstructure so that energy is deconcentrated over large volume, but energy density need to be high as well. That argue for small diameter. So
Yeah.
this has not really been explored in this polymer thing, but I think it's explored in composite. People understood that.
Yeah. Thanks for. I think I asked you a question and you sent me a paper. Thanks so much. It helped to understand how effective the diameter of the fiber. So thank you for sharing that. Yeah. And just ask you also what could be, since you mentioned we don't have a design methodology so far, and maybe the result to be explored. What do you think besides your current research for using entanglement at the design in smaller level? What are the missing maybe parameters do you think may be affecting? Do you think you have to play more on the material side or the structure or the morphology when you try to think where we can push more but beyond what we already done? Do you think, where do you think? Yeah.
Oh, there are many angles to pursue. One angle is entanglements, right? So now after we understand entanglements is doing this, you can revisit the initial design of Jianping Gong, this double network design. So then you can say this in her double network gel, there are two networks. One network has a short chain, another network has a longer chain. So you can almost feel the purpose of the short chain network. Previously, we thought it was just sacrificial. You can say the short chain network is just to get long chain network entangled. So viewed this way, you can rethink this to design. Maybe using single network is hard to introduce a lot of entanglements. Maybe use the two networks or use the particles of one network to enhance entanglement of another network. So how to design entanglements, that become a new game, right? So the other big thing become new game is how to use these materials. So that include manufacturing. So because the material can only be used if you can manufacture it. So yeah, for example, if you have a steel, you cannot just work with steel atoms. You have to think about how you cast the steel, how to bond them together. So the whole technology associated with fabrication from molecules to a device you finally have. People haven't started to do that. So
Yeah.
maybe there are challenges.
Do you think also scaling, if we speak about the design entanglement, if want to scale the design, would be challenging, or how do you see the challenges here for scaling?
You mean scale into larger size?
Yes.
That, yeah, of course, we haven't been engaged in mass production. We don't know. We haven't thought anything obvious. No, actually, one thing obvious is the following. Because the process involves sweating, so you start with very little water. So the polymer, the hydrogel has a high density of a monomer and also polymer, very little water. Before this material is used, we need to put this material into pure water to let it swell to equilibrium. So, and entanglement need to be really, right, to control the final sweating. But that process involves large volumetric change. So imagine if you begin to make a robot, you have to, okay, I first design a small robot, very dense polymer, and swell it into a robot I really have. That probably wouldn't work in robot design. So that kind of issue, yeah, need to think through.
Yeah. So maybe since we're close to the end, I have a few questions. Maybe I'm curious to ask you when it comes to selecting the problems in, especially in soft robotics, we still try to understand how to design tougher soft material. What are the next thing do you think besides toughness in that case that you think very critical besides toughness? Toughness here. Yeah, what is maybe critical also that should be also should be considered? Because I think you mentioned something at the beginning. For example, we use self-healing or other approaches like sacrificial bond. It doesn't work. It doesn't really touch the problem. So when do you try to have like a bigger picture? What do you think besides the problem we discussed today, other problems should be considered and re-examined again? Yeah.
So we don't really develop soft robots in our group. All my knowledge was interacting with colleagues. Robotic colleagues have been telling us, so for design robots, they want material to be elastic. They don't want material keep evolving. So then you have a whole different philosophy of designing robots. So they want elastic material, at least at this stage of development. So now, but we all know if you have an elastic material, usually that material is brittle. So, and to reconcile this, both elasticity, one elastic and tough, this seemed to be a materials issue. Previously, we did not pay much attention. So in metals, people always know that in metal is phrased in the following way. Because for metal, there's a yield condition. Before metal reach yield strength, metal is elastic. That's great, elastic. Very few applications really involve metal repeatedly doing plastic deformation. We don't do that. A robot is hard. You do not cause plastic deformation. Plastic deformation is a failure of robot, right? However, the material become plastic deformed, become tough at a crack tip, because at a crack tip, they can have plasticity. So that's how it works. Maybe at some point, we need to revisit this simple strategy. Just make material really elastic at a stress level you can use, but then allow localized inelasticity. That's still a viable approach. Right now, many designs seem to be a little irresponsible, including ourselves. Just have high toughness at low NOC at any cost, including the application, so that some materials exhibit high plasticity, high hysteresis, even at a very small stress. Then how can anybody use that material? So maybe just to be specific. From a robotics point of view, because there's so many innovation involved in discovery of application. If you have good robots, how you apply it, and construction. So this materials issue become just one of many issues.
Yeah, that's very inspiring. I think that's also advice. If you can, we can consider advice in designing soft robots as well. So thanks so much. I don't know if you have any final words you'd like to say for people listening to. Yeah.
Important thing is a dialogue you are trying to facilitate, because any new applications such as soft robots, you're discovering applications, your new design concept, and possibly new materials. Very few groups really are equipped to deal with all these issues. So people keep saying, okay, we can become multidisciplinary, but people have a finite time. Perhaps a very effective way is what you're doing, just facilitate dialogue among people have different expertise, and maybe some larger research team. So on the team, you can have a different expertise. That was my experience when we were involved in the development of high temperature ceramic engine. And it involve a lot of people. Yeah. So maybe soft robots is still in the very early stage.
That's very important message, and I can't agree more with that. That's so clear, and yeah, you're absolutely right about that point. Yeah, I again, thanks so much. I always enjoy listening to you, and very inspiring as well. Thanks so much, Professor. Thank you.
Thank you. Thank you.